Well, hello. My preferred name is Mela. I'm a biochem student at the University of Texas at Arlington. I've started undergraduate research since January of this year under Dr. Kroll, my mentor, to do research in amorphous ceramics since going to grad school and doing research in the future was within my interests, and I wanted some experience in it. For this summer, I've been working on silicon oxycarbides, which are carbon-containing silicates that consist of glass networks where oxygen and carbon share bonds with a silicon. So SiCO materials possess many different important properties which make them popular in a variety of applications, such as gas separation, drug delivery, and energy storage. In the structure of silicon oxycarbides, the segregated carbon which exists in graphene layers, you can see them in the pictures below, they impede self-diffusion of oxygen and silicon, which results in the mobility of these atoms to differ from a three-dimensional system. So for self-diffusion of atoms in SiCO, we instead assign a fractal dimension, d, to be between 2 and 3. To study this fractal dimension, I will be studying idealized 2D models first, and then I'll be working on models with a fractal dimension and 3D models in the future. So these are the idealized 2D models that I am primarily working on for this summer. In all of them, there is a SiO2 layer, which is the pink layer, which is being sandwiched between graphene sheets, which are the black lines that you would see. So starting from the left, we see that the first three models have the same density, but increasing thickness of the SiO2 layer. In the last model, it has the same thickness as the second model, but it has a greater density of 2.7 grams per centimeter cubed. So with these models, I will be doing heating simulations so that I can study 2D diffusion by extracting the activation energy from the data that I get from molecular dynamics simulations. So for simulations, I start at a temperature at 2000 Kelvin. I increase it with temperature increments of 250 Kelvin until I get to a final temperature of 5000 Kelvin. I'm going to be getting some data such as the mean square displacement of silicon and oxygen. The mean square displacement is essentially a measure of the deviation of the positions of particles with respect to time or steps. So this is the Einstein equation where he related the mean square displacement of a particle with a self-diffusion coefficient as a function of time. We can rewrite this Einstein equation as a linear equation where d prime is the slope when we graph steps versus MSD, like what I did in the graph that you see on the right. So from this graph, I can extract every slope from each individual temperature from the simulation. Each color indicates a different temperature from 2000 Kelvin to 5000 Kelvin. After we get a d prime value from a graph like this, we can use the Arrhenius equation so that we can extract the activation energy. So the Arrhenius equation is a relationship that relates the rates of movements of atoms with temperature or thermal energy. When you take the ln of both sides of the equation, you will have ln of d prime versus inverse temperature. And this will have a slope of negative activation energy over the gas constant. And from this, we can easily calculate the activation energy from the slope. This is basically what I'm doing here in the graph that is on the left. This is for the 13 angstrom model for Si atoms. I extracted the activation energy here, which is 382 kilojoules per mole. and it is the number that you see right next to the M2 column. So I do the same process for all of my models. I compiled all of the data in this table so that I can compare them. So I will also mention that in the graphs that you see on the, for example, on the left, I didn't include certain points because for the calculation of activation energy, we see that there is a noticeable kink in the graph, which is due to a phase change from a solid to liquid as we're heating it. So we notice that in the liquid phase, we see a more linear relationship, which indicates that we are seeing meaningful diffusion here. So we're excluding the points that are within the solid phase. So this is below 3000 Kelvin. So for the trends and the differences in thicknesses and densities, when we look at the table, we see that as density increased, activation energy decreases. And we also see that with increasing thickness, the activation energy will increase as thickness increases. So with these results, we can summarize what we see in 2D diffusion. So again, we see certain trends such as activation energy increasing as thickness increases and as density decreases. We use these results to explore why this is. For example, thickness is affecting diffusion, which is I believe a result between differences in bulk and surface diffusion. So we know that there's a difference between bulk and surface diffusion because of their different environments. Surface atoms are adjacent to carbon layers, while the bulk is not. The thinnest model, where the surface atoms are no longer continuous, exhibits a more ordered structure than the thickest model, which is why I believe this is the reason why we see a difference in activation energy. Also, when we regulated, or I guess when we looked into the temperatures of the graphene layers and the SiO2 layers, we noticed that there was a temperature difference between the two layers. And this may impact why we see differences in activation energies with models of differing thicknesses. So after we explore diffusion in 2D models, the next obvious steps that I could do in my research is to investigate diffusion in models with fractal diffusions and in models where it is three-dimensional. I would also like to run simulations where I can regulate the temperature of the graphene layers and the SiO2 layers so that I can ensure that they are the same temperature throughout the simulation. So that's all that I have for this presentation. I would like to acknowledge some people. I would like to thank Dr. Kroll and my research lab group, which helped me do my research and given me advice throughout my experience and throughout the summer program. I would also like to acknowledge the NSF program and the University of Texas at Arlington for allowing me to have this opportunity to conduct my own research. I'm super glad to be a part of this program, and I hope to be a part of it again next year. Thank you, and that is all.